Welcome everybody to this webinar, which will give you detailed information on how to improve resolution and with this the purity of your target compound. My name is Birgit Götz and I'm Global Product Manager for Purification at Vichy Labortechnik in Switzerland. The goal of everybody who wants to purify a compound is to obtain high resolution and with this minimal of time involved. Now, what is resolution? Resolution is a measure of how well are two elution peaks separated, and it's affected by the distance between the two peaks plus the base width of each peak. And the higher the resolution, the better is the separation. Now, as I said, it's not all about resolution, also time is important. So imagine having several samples a day, as separation should not take forever. So what we say, an optimal time-benefit ratio is obtained with a resolution of around 1. Here you can have some overlap of your peaks, so no clear baseline separation, but on the other side you can expect a shorter run time. But at the end it's up to the chromatographer what resolution is best for his needs. If he doesn't want to lose any of his target compound, he needs to go for a baseline separation, so high resolution, which means more time and at the end also higher solvent consumption. Now, how we are able to control the resolution obtained from a chromatographic separation. The equation of resolution is shown here on top, and as you can see, resolution is affected by 3 parameters: the retention factor, the selectivity factor, and the efficiency factor. So each of these factors have a certain influence on your separation. But how? The retention affects the time a compound interacts with the stationary phase. And the goal is to have your target compound retained at the stationary phase, but not too strong and not too weak. The selectivity factor influences the distance of two peaks. The higher this factor, the better these two peaks get separated. The efficiency factor has an effect on the peak width. And the higher this value, the more narrow are these peaks, and with this the lower is the risk of peak overlapping. All these different parameters have an influence on resolution, but they have that with a different impact, which is shown on this slide. The highest impact has the selectivity, which can be controlled by the mobile and the stationary phase. Lower impact has the efficiency. Here, many different factors have an influence, such as the sample size, particle size, and so on, and we will discuss them later in more detail. With the mobile phase strength, the retention is affected, which has actually the lowest impact on resolution. In general, we can say retention and efficiency are easy control in comparison with the selectivity factor. Screening for the optimal and stationary phase can be quite challenging and time-consuming, but it's so essential. And that's why we immediately start with going into detail here. Selectivity, as I already said, gives us info on the distance between two peaks, so it's a relative measure of the retention of two compounds, clearly visible here from its mathematical equation. In case the two compounds elute at the same time, and therefore they can't be separated, the selectivity factor is 1. And the larger this value, the simpler is the separation, as shown here with these 3 different chromatograms on the left side. Now, how can you influence selectivity? Via the mobile and the stationary phase. And which one you choose depends mainly on your sample, more precisely on its solubility and retention on the stationary phase. And both are affected by the sample's polarity. So as soon as you have a rather polar compound soluble in a mixture of hexane ethyl acetate or DCM-methanol, null phase is the first choice for you. And this means in 90% of the cases silica. If you have a rather unpolar compound soluble in a mixture of water and methanol, ethanol or acetonitrile, choose reversed phase, and here the most common used phase is C18. Now, special types of phases are amino and diol because they can be used in reversed phase and normal phase application. And if you look at their polarity, then it's something between silica and C18. Amino is, for example, ideal for the application of carbohydrates and diol for lipids. And besides this, alumina is a very interesting alternative for normal phase application. It's available in 3 different types, neutral, acidic, and basic, and therefore very useful for basic or acidic compounds. Or for those who have acidic sensitive compounds, try the neutral alumina. As mentioned, screening for the correct condition can be quite challenging, and the easiest way here is actually to use TLC, which is thin layer chromatography. Now, in thin layer chromatography, you're working with a silica coated plate, glass or aluminum, and you spot on your liquid sample at the start position, and you let the solvent run through the plate via capillary action. And you let the solvent run nearly the whole way on the plate, and then you stop. And then hopefully your sample is somehow separated, so you see different spots on the plate. Now, to analyze how well your target compound is separated, you calculate its retention factor RF, which is the solid distance divided by the mobile phase distance. And this RF value should be in the range of 0.2 to 0.5, because this makes your life then much easier later in the preparative method, flash or prep HPLC. Because if the RF value is too low, your compound is too sticky to the stationary phase. So your flash method will take forever to get it eluted, which means a lot of time and solvent. If the RF value is too high, the interaction of the compound with the stationary phase is too weak. So there is a risk of low resolution if using a standard quality cartridge, and you would be forced to spend more money for a high performance cartridge. And besides an RF value in a proper range, you also have to make sure that the spots around your target compounds are as far away as possible to ensure high purity later with flash or prep HPLC. The aim of TLC is to find the most suitable solvent system for your application. And the most common way is actually to try the most commonly used solvents, such as ethyl acetate, DCM, or methanol. And there is nothing against this. And if you're happy with what you see on the TLC plate, go immediately for flash. But perhaps it would be worthwhile to follow the Synder selectivity triangle, which is shown here. In this triangle, several solvents are classified into 3 groups: proton acceptor, donor, or dipoles, parameters which all have an influence on the separating power. And the idea is you choose solvents from these different subgroups in TLC to find the optimal condition for your sample. It's actually like a fine-tuning of your sample system, and this is very useful, especially for complex mixtures. Let's see this example. A mixture of 3 compounds, run with chloroform from the group proton donor, DCM from the group dipole, and tetrahydrofuran from the group proton acceptor. And if we look at the 3 different TLC plates, I think we all agree the best results are given on the right side with tetrahydrofuran, because all compounds are well separated from each other. But if you look at the RF value, it might be a bit too high. So it's running a bit too fast. So what we have to do now is we have to play with the polarity of the solvent. And in this specific case, the compounds are running too fast with the solvent, so they interact too weak with the polar surface of the silica. So now if you want more interaction with the polar stationary phase, we have to reduce the polarity of the solvent. And in this case, we can add some hexane, which is totally unpolar. And as you can see from the TLC plate on the right side, where we use the ratio of 1 to 3, THF and hexane, the compounds are running slower, and accordingly the RF value gets lower and my compounds get even better separated. Now let's say we found the best condition for our sample regarding the solvent's composition. How do we translate now the RF value to a flash method? What does the RF value tell me? First of all, it helps you to determine what quality of cartridge or column is needed to get, for example, a resolution of 1. And the quality of a cartridge is expressed as the efficiency N. Maybe you remember, but anyway, I will talk about this later. So from the RF value of 2 neighboring spots, you can calculate via several equations the efficiency N at a specific resolution. So if you have an RF value in an optimal range of 0.2 to 0.5, as it's given here on the left side, you would need for a resolution of 1 a cartridge with an efficiency of 106. If you have RF values close to 1, as it is here on the right side, you would need a cartridge with a much higher efficiency of 885, which means a high-performance cartridge, which is definitely more expensive than a standard one. Also, with the RF value, it's possible to calculate the column volume, which describes the amount of volume of mobile phase which is needed to elute a compound from a cartridge or column. This is very important then for method development. So in summary, we get a lot of information from this RF value, which shows how useful and important TLC is. TLC plates are available coated either with polar or unpolar material. Usually it's silica or C18. However, silica-coated TLC plates are the most commonly used because they are much cheaper than every other material. So with a TLC plate, we are working in a normal phase condition. So the question is, how do I know from this if reverse phase might be the better choice for my application later in flash or prep HPLC? Let's go through all the possibilities. First of all, if your RF value is between 0.2 and 0.5, choose a silica cartridge. If your value is lower, meaning a too strong interaction with the polar surface of the silica, choose a lower polarity for your flash application or prep HPLC, such as amino or diol. In case you get a very high RF value, the interaction of your compounds with the polar surface of the silica is too weak, and then we recommend to choose C18. And if you want to confirm that, just use a C18 TLC plate. Gradients. For an optimal separation, usually you are working with gradients, meaning you are using at least 2 different solvents of different polarities, a weak and a strong one. By the way, in normal phase, the weak one is the one with the lowest polarities, such as hexane, also called solvent A, while solvent B is the one with higher polarities, for example, ethyl acetate. And in reverse phase, it's just vice versa. So if you are lucky, an isocratic gradient gives you a good separation. This means during the whole run, the ratio of the solvent is the same. And that's easy to handle. But in the most cases, you need to change the solvent polarity during a run for an optimal separation. And this means you start with a weak solvent and increase either stepwise or linear-wise the concentration of solvent B, the strong one. The linear gradient is simple and efficient, but on the other hand, if you compare it with the step gradient, solvent usage is rather high and the loading capacity rather low. But clearly, a step gradient is challenging in optimization. Now, which percentage of your solvents you exactly need to go for can also be screened via TLC by just testing different ratios of the solvents. Our next topic is efficiency. It has also an impact on resolution, but definitely lower than selectivity. And you will see influencing the efficiency is much easier than screening for the optimal mobile or stationary phase. The efficiency is expressed by the number of theoretical plates, N. And this number indicates the performance of a cartridge. The higher this number, the better. Now, what is the theoretical plate? It's actually the theoretical distance for one adsorption and one desorption step. The more steps you get, the higher the efficiency. The smaller is the base width of the peak, and with this, the sharper is the peak. And this is what you need for a good separation. Sometimes people are talking about HETP, which stands for height equivalent to a theoretical plate. calculated via the length of the cartridge divided by the number of theoretical plates. So the smaller this number, the better. There are many factors which affect efficiency, such as mobile phase, stationary phase, solid factors, numerical or mechanical factors. So this is a very complex story. And in the next few minutes, I will focus on just some of those parameters which are especially easy to control. And let's start with the first one, and this is the particle size of the stationary phase, usually the silica. The smaller the particle size in a cartridge, the higher is the total surface, and this increases the possible adsorption and desorption steps, which means the number of theoretical plates. And what you see here in this curve is this effect is getting very strong, especially below 40 micrometer. And here in an example from our application lab, we run the same sample with a cartridge filled with big particles on top and below with small particles. And you can clearly see how the resolution gets improved. So with the 50 micrometer particles, we get 3 different peaks in the first 3 minutes of the run, indicated with the black arrows. And with a small one, we see at least 5 different peaks. And switching and working with small particle sizes is very easy to do, but there is one bottleneck, and that's the effect on back pressure. The back pressure generated during a run is influenced by several parameters, such as flow rate, column lengths, and so on. And as shown here in this equation, the particle size dP as well as the radius r are the biggest factors that influences pressure. The pressure is inversely proportional to the square of both. So decreasing the particle size by half increases the pressure by a factor of 4. So it's very important that you take this into consideration when changing the particle size. Sample size is another crucial parameter which affects resolution. With the loading, you can change the width of a peak. So it's getting broader the more you load. And then at a certain quantity, neighboring peaks start to overlap, as you can see from this example. On the left side, we have a very good separation, high resolution. If we take 10 times more sample, the peaks get closer, and with 20 times more, you see an overlap. At the end, it's up to you what resolution you need, if a certain overlap is a problem for you or not. Because overlap means you're losing some material, but on the other hand, you can load much more per run, so you're much faster and save time and material. The negative effect of the loading on the plate height starts at around 200 microgram of sample per gram silica. But in preparative chromatography, nobody would work with such low loading capacities. They would have forever to get all of their sample purified. Usually we say with 30 milligram sample you get very good separation, but common loadings are much higher, something between 100 and 300 milligram. But this strongly depends on your sample, how easy it is to separate all its compounds. The flow rate plays also a crucial role for separation. And there is another basic equation in chromatography, and that's the one from Van Deemde shown here. It actually describes that the plate height and hence the number of theoretical plates are determined by the particle size and the flow rate. And if you calculate for different particle sizes the plate height at different flow rates, you see here there is a point where you get minimum plate heights at a flow rate at around 0.1 millimeter per second. And with an increase of this flow rate, the plate height gets bigger, so resolution gets lower. But as you can see here from these curves, this effect is stronger for big particles than for small particles. And this actually means with small particles you can speed up without losing much on resolution, and that's the big advantage of small particles. There is a big trend currently to use spherical particles in flash chromatography. Usually this particle shape was used only in analytical chromatography, but meanwhile also flash chromatographers discovered the advantage. Spherical particles can be packed more tightly than irregular ones, and this leads to a more homogeneous flow through the cartridge. And with this, you get sharper peaks. And yeah, with spherical particles, this is another easy way to increase resolution. Now, particles can have different sizes, diameters, but also different pore sizes. Silica is extremely porous. That makes its surface quite big and optimal for chromatographic separation. The standard pore size used in flash chromatography is around 60 to 100 angstrom. That's working for molecules up to 2000 Dalton. For any peptide or protein bigger than 2000 Dalton, these pores are no longer accessible, so the surface for interaction is too small and the resolution is rather low. So for those, we recommend to use large pore sizes, for example, 200 to 250 angstrom. This is another example from our lab where we run peptides of different sizes with standard C18 in green and C18 with big pores in yellow. And what you see here with small peptides, there is no difference, that's on the left side, with both cartridge types. The peptides get eluted between 7 to 8 minutes. For mid-size and big-size peptides, we see interaction with the stationary phase only with the big porous material. With the small pores, the compounds are running with the solvent front and get eluted immediately. And with the big pores, the elution is only after 6 minutes. So the compounds interacted somehow with the stationary phase. So in summary, the larger the pore size, the higher is the resolution for the big molecules. In liquid chromatography, you have two different possibilities to load your sample, either liquid or solid. The liquid loading, which is for sure the easiest way and the most common way for flash and prep HPLC, the sample gets injected via an injection valve or directly on top of the cartridge or the column. With solid loading, which can be used only in flash, the sample, which is a dry or solid mixture of crude sample and a support material, is placed in front of the cartridge. Now, which technique is used when and why? Liquid loading are used for samples which are sufficiently dissolved in the starting eluent. And in general, this is a very fast method, but if you compare it with solid loading with a reduced resolution. The ideal sample quality is around 10 to 30% of the silica weight and the ideal sample volume at around 10% of the purification volume. But this strongly depends on your sample. So for example, how retentive is the sample on your stationary phase. Solid loading is used when your sample is only soluble in the strong solvent, so it's not compatible with the starting eluent. Or it can be also used just to improve resolution because it gives less band broadening and tailing effect. In general, solid loading is a slow method, but it gives enhanced resolution. And the ideal sample quality is 10 to 30% of the silica weight. Now, how is the procedure for preparing a solid sample? What you do first is you dissolve your sample in a suitable polar solvent. You incubate it for some minutes and maybe you're using a sonicator bag to get it completely solubilized. You filter the mixture to get rid of the non-solvent material, and then you add the support material, the silica. Usually it's 5 to 10 times the weight of the crude sample. And then you start evaporation to remove the solvent, but make sure that at the end you have a mixture which is free flowing. And this free flowing mixture is then added in an empty cartridge, which is placed in front of the purification cartridge. Now, why do you have to add a support material? The crude sample gets absorbed on the silica, which allows then a better transfer and distribution of the eluted compounds to the purification cartridge. And it also helps to keep the sample in place and makes it stationary, for example, if you're working with an oily extract. Now we come to the last point, the last parameter, which has an impact and resolution, and this is retention, which has actually the lowest impact. The retention factor has an effect on the time the target compound interacts with the stationary phase, and it can be influenced by the polarity of the mobile phase. The lower the concentration of the strong solvent, the longer gets the separation, and hence we get high K values. Shorter separation times are given with a higher concentration of the strong solvent. And ideal retention factors are between 1 and 5, because this corresponds to our F values and TLC between 0.5 and 0.2. Now we are at the end of this presentation. I hope all this info will help you to make your purification more efficient. Thank you very much for attention.